Bismillahirrahmanirrahim. In this lecture, I am solving problem 2.13 from the book Power Plant Technology by MW Wakil. So, the statement of the problem is a 75 and 750 megawatt. So, in given data, the power of the cycle is 750 megawatt. Operates with turbine inlet steam at 1200 psia. T1 is the inlet steam of turbine, which is equal to 1200 psia, and inlet temperature of turbine is 900 degree Fahrenheit. The condenser pressure is 0.5 psia pound per square inch. Pressure of condenser is P3, which is equal to 0.5 psia pound per square inch absolute. The cycle incorporates three feedwater heaters arranged optimally as one is high pressure feedwater and closed type. Second is intermediate pressure with open type and intermediate pressure. Third is low pressure and closed type. So, and each turbine section has a polytropic efficiency of 90%. Polytropic efficiency of turbine is equal to 90%, which is equal to 0.9 per each section of turbine. And the pump have a polytropic efficiency of 85%. Polytropic efficiency of pump is equal to 85%, which is equal to 0.85. Calculate the mass flow rate at the inlet turbine and pound mass per hour. Number A. Find the mass flow rate of the turbine in unit of pound per hour, pound mass per hour. Part B, these are required values. Mass flow rate of the condenser. Number C, the mass flow rate of the condenser cooling water in pound per hour if it undergoes 20 degree Fahrenheit temperature rise to the condenser. Mass flow rate of the condenser cooling water. Let's suppose this is M.3. Mass flow rate of condenser cooling water. And part D, the cycle efficiency. And in part E, the cycle heat rate and BTU per kilowatt hour. Cycle heat rate and BTU per kilowatt hour. Now we start solution. So initially, to find the required values, first we find the enthalpies and entropies and different required for and different section of the turbine for high pressure turbine, per intermediate section of the turbine, and per low section of the turbine. So first we start from turbine, because in turbine inlet temperature and inlet pressure both are given to us. So first we start from turbine 1200 psi, maximum pressure is 1200 psia. So in turbine P1 is given to us at 1200 psia and T1 is given to us as 900 degree Fahrenheit. First we check whether this is superheated region or insaturated region. So from saturated steam table, at pressure P1 is equal to 1200 psi, saturation temperature is 567.26 degree Fahrenheit, and the temperature given to us is 900, more than this temperature, is T1 is greater than Ts. It means that boiler initial, the entrance stream of the boiler is in superheated region. So we will use a superheated steam table to find H1 and S1. So from superheated steam table, at pressure P1 is equal to 1200 psi and T1 is equal to 900 degree Fahrenheit, enthalpy H1 is equal to 1440.9 BTU per pound mass, and entropy at the entrance of the turbine is equal to 1.5882 BTU per pound mass and per degree R. This is S1. Now for condenser we know that pressure of condenser is equal to 0.5 psia. So here we can find the HF and Hg for the condenser. So from saturated steam table, at pressure is equal to 0.5 psia, HF per condenser is equal to 47.618 BTU per pound mass, and Hg per condenser at 0.5 psia is equal to 1095.9 BTU per pound mass. Now there are three sections of the turbine. One is high pressure section, second is intermediate pressure section, and third is low pressure section. So we will assume the pressure for these three sections between maximum and minimum. It means that maximum pressure given to us is 1200 psi and minimum pressure is 0.5. So for the three section of the turbine, we will assume three values between the high pressure value, this is P1 high pressure value, and low pressure value. So let we suppose pressure per high pressure section of the turbine is equal to 400, pressure per intermediate section is equal to 200 psi, and pressure per low pressure section of the turbine is equal to 50 psi. And now we are calculating enthalpies and entropies for all these sections. So entropy is constant because this is constant line. This is uh, if we draw the Rankine cycle on TS diagram, this will be something like this. This is temperature in degree Fahrenheit, and this is entropy in BTU per pound mass per degree R. This is saturation curve. So the this is the entrance of the turbine. This is point 1, and there are three main sections. Here pressure is 1200 psia, and this is the low pressure part, exit of the turbine. Here pressure is 0.5 psi, and there are three sections. One is 400 psia, second is 200 psia, and third is 50. These two are in superheated region, and this third is 50 psia, and this is the lower section. This is the low pressure section. So this is fraction of mass per low pressure. This is fraction of mass per intermediate pressure, YIP, and this is fraction of mass per high pressure turbine, and this is high maximum pressure at the inlet of the turbine. So this is pump section from 3 to 4. This is point 2, this is 3, this is 4, and this is 1, and we can name this is 1 dash, 1 double dash, 1 triple dash. This is closed type condenser is back to the condenser, and last type is also closed type condenser back to the condenser. So we will find, so entropy is constant at all these values. This is H1 dash S, this is H1 double dash S ideal condition, and this is H2S, and the line for real entropy is something like curve. So on curve, this is H1 double dash, H1 triple dash, and H2. So this point is basically H2S, and here on the curved line basically enthalpy is H2. Similarly, H1 double dash S, H1 triple dash H, and H1 triple dash, H1 double dash S, and H1 double dash. Similarly, H1 dash S and H1. Ideal enthalpy and actual or real enthalpies. So we are finding all these values from the given data. So first we are finding for high pressure turbine, high pressure section of the turbine. High pressure section of turbine, pressure is here, pressure is equal to 600 psia. Sorry, here pressure is 400. I think this assumption is per high pressure, this is 600 psia. Now entropy is constant per R line, so as S1 is equal to S1 S dash, S1 is equal to S1 S dash. This is straight line, isentropic line, which is equal to 1.5882 BTU per pound mass per degree R. So first we check whether this is in superheated region or in wet region. So from saturated steam table at pressure is equal to 600 psia, Sg is equal to 1.4464. So as S1 dash S is greater than Sg. So it means that the region is superheated. It means that the high pressure region of the turbine is in superheated region. So we will use superheated steam table. So from superheated steam table at pressure P pressure P1 dash is equal to 600 psia and entropy S1 S dash, which is 1.5882 BTU per pound mass per degree R. Point, point temperature and enthalpy. So enthalpy H1 dash is equal to, at this point enthalpy will be 1351 H1 S dash 1351. This is S mean this is ideal enthalpy. 1351 BTU per pound mass. And now at this enthalpy we are finding the actual enthalpy. So efficiency, we know that efficiency of turbine is equal to H1 minus H2 divided by H1 minus H2S. This is the formula from the Al-Wakil book. Entropy per turbine, the efficiency per turbine is given to us as 0.90%, 90% to 0.90. H1 is 144.9 minus H2 divided by 1449 minus 1351. So find H2, and this is basically, in our case this is not H2 but this is H1 dash and this is H1 dash S. So in this case H1 dash means actual enthalpy at pressure of 600 psi, which is equal to 1360 BTU per pound mass. Now we are finding the enthalpy at medium pressure section of the turbine. For medium section of the turbine, this is second stage. We know that S1 is equal to S1 double dash S, this line. You can check it on this point, H1 double dash S. Entropy is constant here, which is equal to 1.5882 BTU, this is 8 BTU per pound mass per degree R. First we check whether it is in superheated region or wet region. So from saturated steam table at pressure is equal to 200, this is intermediate stage, psia, Sg is equal to 1.546 BTU per pound mass per degree R. But enthalpy is S1 double dash S, as S1 double dash S is greater than Sc. So this is superheated region. So we will use superheated steam table. So from superheated steam table at pressure is equal to 200 psia, pressure P1 double dash, and S1 S double dash is equal to S1 double dash S is equal to 1.5882 BTU per pound mass per degree R. Find S enthalpy and find S. So entropy 1.5882 is not available, so we will do interpolation. So 8 P1 double dash is equal to 200 psi. This is available in this. You can use superheated steam table. So because in past two problem 2.2 and problem 2.8, I use many times steam table. So this is maybe this will be not difficult. BTU per pound mass per degree R, and steam table these values are available 1.5602 and 1.5943, but we have to find the entropy and 1.5882. So at 1.5602 entropy is 1210.9, and at 1.5943 entropy is enthalpy is 1241. This is enthalpy in BTU per pound mass, and 1.5882 we have to find the enthalpy H1 double dash S. So do interpolation and find H1 double dash S, which is equal to 1256.139 BTU per pound mass. Now we have to find the actual enthalpy at this stage. Now for actual enthalpy, efficiency of turbine is equal to H1 minus H1 double dash divided by H1 minus H1S double dash. So putting values, polytropic efficiency is same for all turbine. H1 is equal to 1440.9. We have to find H1 double dash. H1 is 1444.9 BTU per pound mass, and H1 double dash is 1256.135. So simplify this and find H1 double dash, which is equal to this is basically this value is basically 1235.61. This is basically 1235.61, and H1 double actual enthalpy at intermediate section of the turbine is 1256.139 BTU per pound mass. Now for low section of the turbine, we are finding the entropy per low section of turbine, where pressure, assumed pressure P1 triple dash is equal to 50 psia. So first we check whether it is in superheated region or entropy is same. S1 is equal to S1 S triple dash from the TS diagram Rankine cycle, which is 1.5882 BTU per pound mass per degree R. Now first we check whether it is in superheated region or wet region. So from saturated steam table at pressure is equal to 50 psia, Sg is equal to 1.6588 BTU per pound mass per degree R. As S1 triple dash S is less than Sg, it means this is in wet region. Wet region are mixture of liquid plus vapor between saturated liquid line and saturated. So we will use saturated steam table. So from saturated steam table at pressure is equal to 50 psia, find HF, which is equal to 250.23 BTU per pound mass, and Hg is equal to 1174.2 BTU per pound mass, and Sf is equal to 0.4113 BTU per pound mass per degree R, and Sg is equal to 1.6588 BTU per pound mass per degree R. Now first we find X, dryness fraction from the entropy equation is S1 triple dash S is equal to SF plus X1 plus X Sg minus Sf. So find X here, rearrange this equation, S1 triple dash S minus Sf divided by Sg minus Sf, putting values. So S value of S1 triple 1.5882 minus Sf is equal to 0.4113 divided by Sg is 1.6588 minus 0.4113. So find dryness fraction, which is equal to 0.943. Now we can find H1 triple dash S, H1 triple dash, which is equal to HF plus X Hg minus Hf. The value of Hf is equal to 250.23. The value of X is 0.943. Hg is equal to 1174.2 minus Hf is 250.23. So H1 triple dash S is equal to 1121.53. This is ideal entropy at low pressure turbine. Now we are finding H1 actual entropy, H1 triple dash. Real enthalpy. So for this we use equation turbine is equal to H1 minus H1 triple dash divided by H1 minus H1 S triple dash, putting values. So this implies that polytropic efficiency for all sections of the turbine are same, 0.9 or 90%, and 144.9 minus H1 triple dash divided by H1 is 1440.9 minus 1121.53. So H1 triple dash will be equal to 1153.463 BTU per pound mass. Now we are finding work of turbine for all section. Now work per turbine. So for high pressure section, work of turbine WT1 for first, there are three sections. For first section, this work will be equal to H1 minus H1 dash, which is equal to 1440.9 minus 1360. So work of turbine at first section is equal to 80.9 BTU per pound mass. Now work of turbine for the second section is equal to H1 minus H1 double dash, which is equal to 1440.9 minus 1256.139. So at second section work will be equal to 184.761 BTU per pound mass, and work of turbine per third section is equal to H1 minus H1 triple dash, which is equal to 1440.9 minus 1153.463. So work of turbine for third section is equal to 287.437 BTU per pound mass. So now total work is work of turbine for first section plus work of turbine for second section plus work of turbine for third section. So this will be equal to 80.9 plus 184.761. Gradually work is increases because pressure ratio increases. So work of turbine is equal to 553.098 BTU per pound mass. Now to find net work, we will find work of the pump. So we know that efficiency of pump, formula for efficiency of pump is H4S from the book Al-Wakil minus H3 divided by H4 minus H3, and H4 minus 3 is H4S minus H3 is basically ideal work, ideal work of the pump, WPS. S mean ideal, and H4 minus 3 is basically actual work. So and so WPA, combine these two. So WPA is equal to, and rearrange, WPA actual work is equal to WPS, which is equal to PV del P into V3 divided by efficiency of the pump, which is given to us as 0.85. So now find the pressure difference max. So W actual work of pump is equal to change in pressure. Maximum pressure is 1200 psia and minimum pressure which is given to us is 0.5, and psia mean pound per square inch divided by efficiency of pump is 0.85. But we have to convert this pound inch square per inch square to pound per square feet. So for this multiply it by 144 inch square per square feet, and the value of V3, this is basically 0.016073, 0.016073. Basically V3 is equal to Vf at pressure of 0.5 psia. Find from saturated steam table V3 is equal to Vf, because this is exit of turbine, and exit of turbine is unsaturated liquid line, and at condenser pressure is 0.5 psia. So find Vf at condenser at 0.5 psia from the steam table, which is 0.016073 feet cube per pound mass. And to convert this value into B2U, multiply by divide by 778.169 pound mass per BTU. This is conversion into BTU. So this pound mass will be cancelled with this pound mass. Here inch square inch will be cancelled with square inch. Foot square will be equal with square, 1 foot will be left here. So and now BTU per pound mass is left, and calculate this value. So WPA will be equal to actual work of the pump will be equal to 4.19 BTU per pound mass. This 778.168 conversion to BTU unit. Now net work, we can find net work done is equal to work of turbine minus work of pump. So work of turbine is 553.098 minus work of pump is 4.19. So net work is equal to 548.908 BTU per pound mass. Now first value which is required is mass flow rate of the turbine. So first power is given to us and the problem is 750 megawatt. So first convert this value into BTU per hour. So 750 megawatt is equal to 750 into 1000 kilowatt, and 1 kilowatt is 1 kilowatt is equal to 3412.142 BTU. So convert kilowatt into BTU per hour. So it means it multiply by this value to convert kilowatt into BTU per hour. So power is equal to 750,000 multiplied by 3412.142 BTU per hour. So power will be equal to 2559 106 500 BTU per hour. Now we can find m dot of turbine. So as power is equal to m dot of turbine multiplied by net work. So m dot T is equal to power divided by network. So power is 2559106 BTU per pound mass, and network is 548.908 BTU. This is BTU per hour, BTU per pound mass. So this BTU will cancel with BTU. So net m dot T will be equal to 4.662 multiplied by 10 power 6 pound mass per hour. So this is the answer of part A. Now we are solving part B. So in part B, mass flow rate of condenser is needed. So for mass flow rate of condenser, basically mass flow rate of condenser, there are three sections. So for mass flow rate of condenser is equal to 1 minus y HP minus y intermediate pressure minus y low pressure into m dot T. It means that basically this is the fraction of mass used in high pressure section of the turbine. This is the fraction of mass used in intermediate pressure, and this is the fraction of mass used in the low pressure section of the turbine. So entrance mass to the turbine is 1 pound mass. Some fraction is expended in high pressure, some fraction is expended in intermediate pressure, and some fraction is expended in the low pressure part of the turbine, and the remaining is go to condenser for further uh, working of the turbine. So we will subtract these values because these are expended in the turbine, and the remaining section is used in the condenser, and we will find these values from the energy balance equation, and those energy balance equations are too complicated, means that three equation and three unknowns. So we will solve these values in matrix form. So, we will convert them into matrix form, and this we will solve. So this that will in other problem. So I am assume these values uh, these to find these values are not difficult but too much lengthy, so I am assume these values are almost 0.1 or 0.06. so y high pressure turbine, I assume this value is 0.06, y intermediate pressure is 0.11, and fraction of mass used in low pressure turbine is 0.07, multiply by mass of turbine, mass flow rate of turbine is 4.662, multiply by 10 power 6 pound mass per hour. So mass of condenser is equal to 3.54 multiplied by 10 power 6 pound mass per hour. So I assume this value you can find from the energy balance equation. So in energy balance equation there will be three equation and three unknown, and you will solve all these. But uh, but I assume here these videos. Now at point C, mass flow rate of the condenser cooling water. Mass flow rate of the condenser cooling water is needed. Let's suppose this is M.3. So we know that Q condenser is equal to M dot condenser into H3 minus H2. So H3 is basically unsaturated vapor line. H3 is equal to HF at 0.5 psia, and this is equal to 1153.463, and H2 is basically in the uh, exit of the turbine. H2 is basically this point here, exit of the turbine. So we will find this value. Basically this point is basically this is pump. Basically this is pump and this is expansion. So this is the pump and this is the turbine boiler. This is the boiler part. From port to 1, this is the boiler part. Now this is H2. So H2 is in the wet region. Basically H2 is in the wet region. So we will use a saturated steam table to find H2. So for H2, we will find entropy, and then we will find H2. So for H2 we will do some calculation. So S2 is equal to SF plus X Sg minus SF at 0.5 psia, at 0.5 psia. So S2 is equal to S1 use and start. So S2 is equal to 0.5882, which is equal to SF is enthalpy of liquid at 0.5 psia, which you can find from the saturated steam table. 0.0925 plus X and Sg minus SF. So Sg is equal to 2.0866 minus SF is 0.0925. So find X from this equation. So X is equal to 0.75. Now find H2S. H2S is almost equal to H2, so I assume that this is H2. So H2 is equal to HF plus X Hg minus HF. So HF at 0.5 psi is 47.618, X is 0.75, and Hg is 1095.9 minus HF is 47.618. So find H2 from this. So H2 is equal to 833.829. Now you can find heat transfer and the condenser. So heat transfer and the condenser now is putting values in the above formula. So m dot of the condenser, which is basically 3.54 multiplied by 10 power 6 pound mass per hour, N2 H3 minus H2. So H3 is 1153.463 minus 833.829, and to unit is BTU per pound mass. So pound mass will be cancelled with pound mass, and heat transfer and the condenser is heat rejected and the condenser is 0.5 1.13 multiplied by 10 power 9 multiplied by 10 power 9 BTU per hour. Now we can easily find mass flow rate and the uh, cooling part of the condenser. So which is equal to m dot Cw or m dot 3 is equal to Q in condenser divided by Cp del T. This is the equation. Q is equal to mCp del T. So this is 1.13 multiplied by 10 power 9 BTU per hour divided by Cp per water is 1 BTU per pound mass into degree Fahrenheit, and temperature difference is given to us as 20 degree Fahrenheit. So degree Fahrenheit will be cancelled with degree Fahrenheit, and the unit will be equal to m dot Cw will be equal to 1.13 multiplied by 10 power 9 divided by 20. This will be equal to 0.565 multiplied by 10 power 8 BTU per hour. Sorry, pound per hour. BTU will be cancelled with BTU. So this will be equal to pound per hour. This is the mass flow rate of cooling water in the turbine. Now in part D we will find cycle efficiency. So cycle efficiency is equal to net work divided by heat supplied in the boiler. So net work is equal to 548.908 divided by 1190.67 multiplied by 100, and this Qn is equal to H1 minus H1 triple dash, which is equal to 1440.9 minus 250.23, which is equal to 1190.67 BTU per pound mass. So multiply by 100. So cycle efficiency will be equal to 46.1%. This is the end of the part D. Now we are solving last part number E. In part number E, cycle heat rate is required in the unit of BTU per kilowatt hour. So we know that cycle efficiency is equal to net work divided by Qn. So I can write this value as Qn, rate of cycle heat rate is Q divided by W. So Qn divided by net, take reciprocal, so this will be 1 over cyclic efficiency. Now basically this is heat rate. So heat rate is equal to 1 over cycle efficiency, and the unit of Qn is BTU per hour, and this is also BTU per hour. So hour will be cancelled with hour, and heat rate is equal to 1 over cycle efficiency. Cycle efficiency is 46.1%, so 46.1% is equal to 0.461, and this is BTU, and we need this in BTU per kilowatt hour. So convert this BTU into kilowatt hour. So convert this BTU into kilowatt hour. So as 1 kilowatt hour is equal to 3412.142 BTU. So 1 BTU will be equal to 1 over 3412.142 kilowatt hour. So heat rate will be equal to 1 over 0.461 BTU, and convert this BTU to kilowatt per hour, which is equal to 1 over 3412.142 kilowatt hour. So heat rate is equal to, this is in double division, so I can write this in denominator, divide by 0.461 BTU per kilowatt hour. So final answer of heat rate is equal to 7401 BTU per kilowatt hour, and this is the end of the problem. And please like and subscribe my YouTube channel and share with your friend. Thank you.